Okay, so I emailed you guys a practice worksheet. Hopefully we worked on it. If you haven't, work on it before you listen to me, okay? It helps a lot more if you've already worked on it when I go over it. All right, so let's do number one. So number one, and hopefully you've done it. What is the order of this reaction with respect to the reactant hydrogen peroxide, and how do you know? This is interesting. They give you graphs. So you need to figure this out based on the graphs. Now I need you to think back to when we went over integrated rate law. We said that we have a rate law, and what we did, we had to integrate the rate law, and then we rearrange the rate law to get a linear equation to be able to get a linear plot. You guys remember that? Okay. Now, when you look at these three graphs, this is the only one that has a linear plot. Now, think about, I actually put up the graphs for that. It's in your notes, but I'm going to put it up again to make sure we're on the same page. These are the three graphs. If we had a zero order reaction, if we plot concentration of A over time, we would get a linear plot. Now here, when we graph the concentration of hydrogen peroxide over time, we did not get a linear graph. So it is not zero order. If it is a first order, if you take the ln of the reactant over time, you would get a linear graph. Look over here. When we take the ln of hydrogen peroxide over time, we have a linear plot, right? So what we have here, we have a linear plot. Now, it is not second order reaction, because if it was second order reaction, if you plot 1 over A over time, you will get a linear graph. When I come over here, when we plot 1 over concentration of hydrogen peroxide over time, we don't get a linear plot. So what order is this? This is first order. Again, why is it first order? Because when I graph ln of hydrogen peroxide over time, I get a linear graph, and I don't get that for the other two. So this is a first order reaction. You have to figure it out based on the graph. Okay, now the second one, it says, what is the integrated rate law? You know that, you have it in your notes. What is the integrated rate law for the first order reaction? Is ln concentration of hydrogen peroxide at times T, that's how much is left over concentration of hydrogen peroxide at the beginning, equal minus KT. This is the integrated rate law for first order reaction. And we just found out that this is a first order reaction. Okay. Now, what is the rate constant K? If you remember that the rate constants are the slope, right? The slope or the rate constant. The slope or the rate constant. So if we come over here, the slope is going to equal minus K, is minus because it's going downward, right? So the slope or the rate constant, the slope or the rate constant. So how can we find out the rate constant? Based on the graph, we can find the slope. You find the slope, you have the rate constant, right? You find the slope, you have the rate constant. Okay, so minus K is my slope, and you already know how do you figure out the slope. You figure out the slope based on rise over run. Yeah, the good old days. Rise over run, this is how you figure out the slope. Okay, so to figure out the slope, what I'm going to do, what you need to do, you need to pick 2 points, right? We need to pick 2 points, and then we're going to do rise over run for those 2 points. y2 minus y1 over x2 minus x1 for the 2 points. Now, you may pick points that are different than mine. I'm gonna pick 2 points. The 2 points that I'm gonna pick times 0 and I'm going to pick time 3600. Those are the 2 points I'm going to take. You guys are good so far? Okay. So those are the 2 points I'm going to take. All right. Now, again, what I'm trying to do one more time, if the slope in this on this graph, the slope is going to tell me what the rate constant is. So what I'm doing, I'm picking 2 points on this graph. I want to pick point at 0 time, okay? At 0 time, and I'm going to pick a point at 3600 seconds. So far, so good. Okay. Now, what I have to do, if I take this, again, it's going to be 0. And if I take this one over here, this is going to be around 0.5. Again, I don't even need to read that. What I could do, I could just come up here and I could read the numbers over here. I can just read the numbers over here. This would be -3 and this would be 0. So far so good? You guys got this down? Okay, so again, I just picked 2 points on the graph. All I did, I just picked 2 points on the graph, and you can try to read it based on the graph, but if you have a table, why not to read it based on the table? Let me do that because that's a lot better than what I just tried to do. We're good so far? Okay. So I'm going to repeat it one more time since I just confused the heck out of you a little bit. So we know that the slope is going to give me the K, the rate constant. Now what I'm going to do, I'm going to find the slope of this linear plot to find out K. How do you find the slope? Rise over run. What do, you pick 2 points. You pick 2 points and you do rise over run. The 2 points I'm going to take, I'm going to take a point here, I'm going to take a point here. I took time 0 and I took time 3600. It doesn't matter which one you take. And then you can try to figure out based on the graph, but hey, I have a table. If you have a table, go based on the numbers on the table. That's a lot easier than trying to read the graph. All right, so what I have is minus 3 minus 3.00 minus 0.00. Okay, well I got these from here over 3600 second minus 0 second. Okay, so I did this minus this and this minus this, this minus this, this minus this. All right, so far so good. Beautiful. So if I plug it in for 2 sig fig, don't forget the sig fig, don't forget the sig fig. For 2 sig fig, what I end up getting, I'm going to end up getting 8.3 times 10 to the minus 4. That's going to be my slope. Now, you tell me, what is the unit for K? First order reaction is 1 over S, 1 over time. Beautiful. All right, next one. What would be the concentration of hydrogen peroxide at 4,500 seconds? Now, check this out. In this question, they ask you for concentration. They ask you for concentration and they give you time. Okay? I need you to remember this and think back. We said that the reason we have integrated rate law is because integrated rate law does what? It relates concentration and time. So integrated rate law, the whole point of it is because it relates concentration and time. It relates concentration and time. Just the normal rate law couldn't give us that correlation, but the integrated law, we integrated so we can have some idea about time and concentration. Well, look at this question. This question, they give you time, they ask for concentration. So what do I need to do? I need to write the integrated rate law. So I'm going to write the integrated rate law. That's the first thing I'm going to do. So it's going to be the hydrogen peroxide at T over the hydrogen peroxide at the beginning equals minus KT. Okay? Now, let's go over this. So what they're trying to add, what they're asking you right now, what is my X? Always figure out what's your X. The concentration of peroxide at 4,500 seconds. So this one right here, that's my X. Which means I have to be given everything else, right? Which means I have to be given everything else. So ln of X. Now, what is the concentration of hydrogen peroxide at the beginning? The concentration of hydrogen peroxide at the beginning is 1 molar. I don't need the ln. I just want at the very beginning, what is the concentration? The concentration is 1.0. Again, I'm not using this value because this value was to graph it. We graphed it. But here, what I need is the concentration at the beginning, which is 1. Equals. Now, the K we just found out from our last question. Okay? So what I can do, I can figure out. And T, what is my T? My T is my 4,500 second. Because I could so far. And check this out, the unit does match up because the unit for my K was S and they give me seconds, so I can cancel those out. Yeah? Okay. So this is good. This is really good. So once you plug it in, what are you going to get for X? For X, what you're going to end up getting, you're going to end up getting 0.020 molar. That's going to be my X. Yeah? Okay. Now again, this was the kind of problem we haven't done many. Look at the graph and answer the question. What you really had to remember was that the slope will give you the rate constant. And once you have the rate constant, you can just plug it in the first order integrated rate law. Nice. Ready for next one? Okay. This was, and don't forget this graph. This was our next problem. In this problem, what I gave you, I told you this is first order. So I kind of made it easy for you. I already told you this is a first order reaction. And I gave you the half-life. Okay? I tell you it's first order and I give you the half-life. Part A. Using the definition of half-life, approximately how long will it take for 95% of the original amount to disappear? Give a range. Okay? Now, here they don't give you solid numbers. They say percentage. Every time they give you percentage, make up numbers for yourself. Right? Percentage is not an amount. Percentage is a ratio. Remember that. Percentage is a ratio, is not an amount. But you can make up number for yourself easily. So it says, how long does it take for 95% to go away? So which means what? How much is remaining? 5% is going to remain. Okay? So 5% is going to be remaining and 95% is going to disappear. You guys are good so far? Okay. And it says, give a possible time that this is going to happen. Okay. Now, like I said before, I love making up numbers. So, can I say that I start with 100 grams? Why not? I start with 100 grams. Now, what is the definition of half-life? Half-life is the time that it takes for half of the reactant to go away. So it's the time that you take that half the reactant is going to go away. So after 28.25 minutes, half of whatever we have is going to go away, right? Okay. So what's going to happen after 28.25 minutes? How much do I have left? Now I'm going to have 50 grams left. Do you guys agree? Because that's the definition of half-life. The time that it takes for half of the reagent to disappear. Now, after another 28.25 minutes, what's going to happen? Now it's going to become half again. What is half of 50 grams? 25 grams. I like doing it this way because I really want you to understand the definition of half-life. So now I have 25 grams. What do you think is going to happen after another 28.25 minutes has passed? That's going to become half. What is half of 25? Is 12.5. Okay? Now, another 28.25 minutes is going to pass. What's going to happen? This is going to become half. What is half of 12.5? Is 6.25. Okay? Now, another 28.25 minutes is going to pass. This is going to be half of that. Half of that is 3.1 grams. Okay? So check this out. I started with 100 grams. You can start with whatever number that you want. 100 is an easy number, right? So 95% is going to disappear. 5% is going to remain. So when does that happen? Somewhere right here, right? Because if I start with 100 grams, the 5% remaining would be 5 grams, right? 5% remaining of 100 grams, it would be 5 grams. So it would be somewhere here. Somewhere here, I'm going to have 5 grams. Somewhere there, I'm going to have 5 grams. And that's what it gives you it tells you to give a range. Are we good so far? Okay. Now, 1, 2, 3, 4. Did you guys see that? 1, 2, 3, 4 half-life. 1, 2, 3, 4 half-life. So if I take 4 times 28.25 minutes, what I'm gonna get? I'm gonna get, let me see, 113 minutes. Okay? 1, 2, 3, 4, 5 now. If I do 5 times 28.25 minutes, that would be 141.2 minutes. Okay, they ask you to give you a range. We said somewhere here, that's what's going to happen, right? Somewhere here, we are going to have 5 grams left. So, the range would be somewhere between 113 minutes to 141.2 minutes. Somewhere in there, somewhere in that range, I'm going to have 5 grams left. So far, so good? Okay. Now, what I wanted you to get out of this is that whenever you have percentage, it's not an amount, it's a percentage, it's a ratio. You can make up numbers. The easiest thing is to make up 100 because 100 is easy. Because if I have 100 grams, 5% remaining would be 5 grams. And also I wanted to show you what half-life means. It means the time it takes to become half, to become half, to become half, to become half. Yeah? Okay. What is the rate constant K for this reaction? This one you know. I already told you it's a first order reaction. And I've given you half-life. So I've given you all the hard stuff. So if I know it's a first order reaction, the first thing I'm going to do, I'm going to write down the half-life equation for a first order reaction. Okay? I have the half-life. So all I have to do, I just have to plug it in. What the half-life is, the half-life is 28.25 minutes equal 0.693 over, now I'm trying to figure out what K is. So what my K is going to be 0.02454. What's the unit? 1 over minutes. It's first order reaction and our time is minutes. Yeah? Okay. So now I have the K. Every time they give you half-life and you know it's a first order reaction, you can easily figure out the K. Okay, let's go to the next part. Okay, so part C, it says using the integrated rate law for a first order reaction. Now the key is, again, I'm telling you it's a first order reaction. You don't have to figure it out. And then how long would it take for 95% of the original amount of the reactant to disappear? So we talked about this, how long. What did we say? We said every time that they ask you for how long, what do you use? You use integrated rate law. I mean, this question also just tells you that you use integrated rate law. But if I didn't tell you this part, remember, every time they ask you how long, you have to use integrated rate law, because integrated rate law relates time and concentration. Okay, so I know it's a first order reaction, and I know that they're asking me how long, so I have to use the integrated rate law. So I'm just going to write down the integrated rate law for the first order reaction. Be ln concentration of A at times T over concentration of A at the beginning equals minus KT. Okay? Now, if you remember, T was how much is left. And this one means at the beginning, right? How much you start with. So how much you start with and then how much is left. Okay? And how long is what you're trying to figure out. So T is Rx. It really helps to figure out at the beginning what is your X. Okay? Because once you figure out what is your X, you have to have other variables to plug it in. They can't give you two variables at a time, right? So once you know what's your X, and you know you have to have every single piece of information that you need to figure out T. Alright, so here's the thing. I don't have numbers, but I just have a percentage. It says 95% is going to disappear, right? So if 95% is going to disappear, that means what? 5% is going to remain or to left. 5% is going to be left over. Do you guys agree? So 5% is going to be left over. So what I can do, again, I can just make up numbers here. Shall we do this? Yeah, let's just make up numbers here. So I have ln. I know 5% is going to be left over. So I can say I start with 100 gram and I end with 5 gram. That would be 95% disappearing, right? I can say that I started with 5 gram, concentration of 100, and then I ended up with a concentration of 5. Can I say that? Sure, because if 95% is going away, if I start with 100 molar, I'm going to have 5 molar left. Can I do that? Sure, I can do that. Equals minus, I have K from the last part of the problem, 0.02454 over minutes, and then I can solve for X. If I do that, if I solve for T, what I'm going to end up getting is 2 sig fig, don't forget the sig fig, is going to be 120, what's the unit? 120 minutes. Now, I want to go back to this again. This is the hardest part of this question. So again, 95% is going to disappear. If 95% disappear, that means 5% is going to be left over. Yes? Yes. 95% is going to be gone, 5% is going to be left over. Now here, this is how much you start, this is how much you left. I know that 5% is going to be left. So I'm just going to make up number. If I start with 100, that means 5 is going to be left over, because that would be 5%. So you can use whatever number you want as long as this ends up being 5% left, right? As long as this number ends up being 0.05, because 5% left divided by 100 it will be 0.05 is going to be left, as long as you take ln of 0.05. Yeah, because that means 5% is left. Okay, so hopefully you're following so far. Now let's go to the next one. If the initial concentration of A is 2.50, what is the concentration exactly after 3 hours? That's fine. Now again, when you read this question, I want you to tell me that there is concentration and there is time. Every time there is concentration and there is time, you know we're going to use integrated rate law. We're using that so much. Hopefully you're getting this down at this point. Alrighty. I don't know, is it first order reaction? Because I had told you in the previous part. Now, what is my X here? You have the initial concentration. You have the time. You're trying to figure out the concentration is going to be left after 3 hours. So what is my X? My X is this one right here. Again, I know I'm repeating myself, but I want to make sure you really understand this. I'm showing you not only how to do it, I'm showing you how to approach every problem. Okay, hopefully this will help. So figure out what's your X right off the bat. So ln, this is my X because they're asking me what's the concentration after 3 hours. Initially is 2.50 molar. I have K again from part B, 0.024541 over minute. Now they give me hours, right? But remember, I have to plug in minutes because my K is minutes. Your constant dictates your units. Your constant dictates your units. Okay, so 3 hours would be how many? 3 hours would be 180 minutes. So 3 hours would be 180 minutes. And this is cool because then the minute's going to cancel out. Now what do I end up with? Again, don't forget what my X is. That is my X. Alright, so if I plug it in, what I'm going to end up getting, I am going to end up getting 0.0302 molar. That's what's going to be the concentration after 3 hours. We're good so far? Okay. Nice job. Ready for last part? We're almost there. What is the reaction rate? So in this question, they ask you just for reaction rate at exactly 3 hours, assume the reaction is not reversible. So they ask you for reaction rate, not the integrated rate law. So what they're asking you is just for rate law. They're asking you just for rate law. It's been a while since we had that. They're asking you just for rate law. And you know, rate law would be what? The rate constant times concentration of A, and you know is to the power of 1 because it's a first order reaction. Okay, so far so good. Okay. Now, they ask you for rate, so we don't have rate. That's going to be my X equal, you know the constant, right? 0.024541 over minutes. And then you know the concentration of A because they're asking you the concentration of A at exactly 3 hours. We just found out in the last question what that concentration would be. So times 0.0302 molar. Okay. So if I do this, what I end up getting for X, I'm going to get 7.41 times 10 to the minus 4. What's the unit? The unit for rate law is always, the unit for rate is molarity over time. And in this case is minutes. Molarity over time. Don't forget that. Yeah? Okay. Ready for last one? Let's do it. Let's do our last problem. Before we write last problem, so the hardest thing about this question, was you figuring out that I didn't give you a number, but I gave you this 95%. And a 95% is not an amount, it's a ratio. So you can make up any numbers you want. That's what I usually do to end up being 95%, right? So, or just say 95% is going to be gone. 5% is going to be left. That's 0.05, right? The way I like it is like I have 100, 5 molar is going to be left over. That's 5%. Okay, last one. I give you a table. We've done experiment. You know, every time you have experiment, you're going to figure out the rate law, right? You're going to figure out the rate law. Now, one thing that you should always remember is that when you're trying to figure out rate law, rate is equal K, concentration of, times concentration of the reactant, which is I minus, and S2O8 minus 2. Okay, so rate is equal rate constant times the concentration of the reactant. Now, what do I need to figure out? What just happened? I need to figure out the orders. What is the order of I minus? What is the order of S2O8 minus 2? Okay, again, remember, to figure out the orders, you have to do experiment, right? To figure out the orders, you have to do experiment. And this is what they've given us the experiments to look at. Are you ready? Okay. Let's look at what's going on. And it's been a while since we've talked about this. Remember, to look at it, you have to pick 2 experiments that where only one variable is changing, right? You have to pick 2 experiments that only one variable is changing. You can't change 2 variables. Wouldn't work like that. Let's see. I want to figure out I minus. Which 2 experiments should I look at? What do you think? I should look at experiment or trial. Let me call it trial since I call it trial. I should look at trial 1 and 2, right? Why 1 and 2? Because in 1 and 2, S2O8 minus 2 concentration remains constant, and the only thing that is changing is I minus. That's what I want. So what happened? What they do, they half the concentration. The concentration goes down by half. What happens to the rate? They go from 12.5 to 6.23. Also goes down by half. Okay. Now, you know what that means. If the concentration of I goes down by half and the rate also goes down by half, what does that mean? What do we have? That means we have a first order reaction for I minus. Alright, so far so good. Now, the next one is S2O8 minus 2. Which 2 trial are you going to look at? You're going to look at trial 1 and 3, because if you look at the trial 1 and 3, the I minus remains constant, and that's good. So now let's look at here. And S2O8 is changing. It goes from 0.04 to 0.02. Okay, also goes down by 2. Now what happens to the rate? Oh, the rate also goes down by 2. You guys see that? Okay, so the S2O8 minus 2, the concentration goes down by 2, the rate goes down by 2. What does that mean? Also first order is also first order, right? Yeah. Alright, so we're in a good shape. We figured out the order. So what is going to be rate? Rate is going to be K constant times concentration of I minus to the power of 1. That's the order. Times concentration of S2O8 to the power of 1. Okay, those are the orders. We're good. This would be our rate law. Next question, it says, using data from trial 1, determine the rate constant K. It doesn't matter which trial, which experiment you pick. to figure out rate constant. When here I told you one, so like we're on the same page. But if I hadn't told you use trial one, you can use any of them. You can use any of them to figure out the rate constant. Okay. Now, you know how to do this because the hardest part of this was to figure out a rate law. Once you have the rate law, then you can use any of the trial to plug it in and figure out what K is. Ready to do this? Okay. So, again, don't forget my rate law is rate is equal K times I minus concentration to the power of 1 times S2O8 minus 2 concentration to the power of 1. That's good. Now what I'm going to do, so I'm just going to use trial 1. This is my rate 12.5. 12.5 times 10 to the minus 6. I'm trying to figure out K. I minus concentration is 0.08. 0.080 to the power of 1. S2O8 minus 2 concentration is, look it over here, 0.040 to the power of 1. Again, all you have to do is just go to that trial and plug in the numbers. All you gotta do. So if I do that, what I'm gonna solve for K, what my K is going to be 0.0039. Okay. Now, what is the unit? What is the unit for this K? 1 over molarity times minutes. Remember, the units have to cancel out to end up with rate, and the rate is always molar per time, which in this case it was molar per minute. And this is molarity, and this is molarity. So far so good. Okay, I've gone over this a lot, so make sure you're getting this down, that this has to be the unit. Okay, beautiful. Nice job for hanging in there so far. All right, last page. It really is the last page. Determine the initial rate of if I minus is 0.120 molar and S2O8 minus 2 is 0.150. Okay. Now, because you have the rate law and you have the rate constant, then you can figure out what's the rate if I give you different concentration, right? And one thing I just want to make sure I'm on the same page, we're not talking about integrated rate law because we're not talking about time. We're talking about rate and concentration. Every time we talked about rate and concentration, what do we have to use? We have to use just the rate law. Integrated rate law comes into play when we add in time, how long something takes. Okay, so far so good. All right, so I know the rate law, and that was the hardest part of this problem. Once you figure out the rate law, everything else is easy, and they both are in to the power of 1 because they're both first order. So I'm trying to figure out what would be my rate. I have the K from the previous problem, 0.0039 molarity over minutes. Concentration of I is 0.120 molar. And then, what did I just do? I don't know why I did this. I was just testing you guys out. You're probably like, what is she doing? There we go. Times S2O8 minus 2 is 0.15 molar. Okay. Are we good so far? Okay. Now, are you going to solve for X? When you solve for X, what are you going to end up getting is 7.0 times 10 to the minus 5. What is the unit? Molarity over minutes. Molarity over minutes. That has to be the molarity over minutes. And I want you to look at how these cancels out. So I have molarity and molarity goes away. One of the molarity goes away. I end up with 1 molarity over minutes. And that's why I have here 1 molarity over minutes. So 1 molarity goes away. I end up with 1 molarity over minutes. And that's my rate equation. Remember, the constant has to cancel out the rest to end up with molarity per minute. Okay, ready for last one? Oh, 2 more, but I like this last part. Could the overall reaction above be an elementary step? Yeah? Okay, so what do you think? Could the overall reaction above be an elementary step? So they're talking about this reaction. They say, could this reaction be an elementary step? Now, here's what I need you to remember for the elementary step. Okay? For the elementary step, if you remember to have an elementary step, because elementary step was 1 single step, we said you can use the coefficient as an order. You guys remember that? So for an elementary step, the coefficient, the stoichiometric coefficient would be the order. And the reason that was the case, because it was 1 single step. So because it was 1 single step, the coefficients could be the order of the reaction. That was going on if you had an elementary step. Okay, so hopefully you remember that. I'm going to repeat this one more time. So if you remember, what we said was that for the elementary step, because it's a single step, the stoichiometric coefficient would be the order. The coefficient would be the order. Okay? So if this was an elementary step, that means the order for I would be 2 and order for S2O8 would be 1. Because for the elementary step, you can use a coefficient as an order. So if this was an elementary step, that means I would have an order of 2 and S2O8 would have an order of 1. But when we do experiment, based on experiment, which is more accurate, based on the experiment, I has an order of 1 and not order of 2. So no, this cannot be an elementary step. Because if this was an elementary step, the I minus would be a second order. But we know that's not true based on the experiment. If you do experiment, we know that I is only first order. And also, I need to remember that we said it's very rare for 3 things, 2I and then 1 S2O8 minus 2, to come together at the right orientation with enough energy for this reaction to happen. Most of the time, things don't happen in one step. This is not a one-step reaction, because you have to have 3 things come together at the right angle, at the right time, the right energy to have that to happen. That's very, very rare. So the answer would be no, this is not an elementary step. How many particles collide in the rate determining step? Okay, how many particles collide in a rate determining step? So we establish, again, pay really close attention because I know these are not easy. We establish that this is not a one-step reaction. Okay? So it's going to have a couple of steps at least until the reaction happens. And if you remember, based on the mechanism, the rate determining step, the RDS, that's the slow step, will determine the rate law for the reaction, right? So the rate determining step, that's my slow step. That's what controls the rate. That's what's going to tell me what is my rate law. Controls the rate is going to tell me the rate law. So when you look at the rate law, based on experiment, based on the rate law, the order of I is 1 the order of S2O8 is also 1. So based on the rate law, because remember the RDS, the slow step, that's what controls the rate, and that's what gives us the rate law, because the other one goes pretty fast. So based on the rate law, if you look at the rate law says two particles are going to collide together, one I minus and one S2O8 minus 2. So based on that is going to be two particles. Is going to be one I minus and one S2O8 minus 2. I want to repeat this one more time. So remember, we said most likely this is not going to happen in one step, right? We know that's not true because the orders, the coefficient don't even match the rate based on experiment. So there's got to be a couple of steps for this reaction to happen. Now, when that's the case, the slow step, the rate determining step, controls the rate. And that is going to tell me to dictate what is my rate law. Now, the rate law is this one right here. So based on the rate law, at RDS, we had two particles. One was I minus, the other one was S2O8. So we figured this out based on the rate law. So based on rate law, because the rate law says we have I minus to the power of 1, S2O8 to the power of 1. So based on the rate law, we have two particles. One is I minus and then one is S2O8 minus 2 at RDS, in our RDS, at a slow step. Yeah, okay. Alright, so this was a really good worksheet. I'm not just saying that because I gave you the worksheet, but it reviewed a lot of things that we've talked about a little while ago. So make sure you understand this. Ask me if you have any questions, and we'll move on to the next chapter. I'll see you guys next time.